Problem 5.2, it is based on ideal and actual Rankine cycle. Problem statement goes like this. Steam at 20 bar and 360 degrees Celsius is expanded in a steam turbine to 0.08 bar. It then enters a condenser where it is condensed to a saturated water. The pump feeds back the water into the boiler, and in this way cycle gets completed. Assuming ideal processes, find number 1 for per kg of steam the net work and the cycle efficiency. Number 2, if the turbine and the pump have each 80% efficiency, find percentage reduction in the net work and cycle efficiency. In order to solve this numerical, let us first represent the ideal as well as actual Rankine cycle on TS, temperature entropy and enthalpy entropy diagram. This is temperature entropy diagram and its curve is like this. This is enthalpy entropy diagram and its shape is like this. Now first let us determine the condition of steam which is leaving the boiler and entering the turbine. So at 20 bar 360 degrees Celsius is the temperature of the steam. By seeing this value, it seems that the steam might be superheated steam. So assuming the given condition of the steam is superheated, now I am drawing the Rankine cycle on TS and HS diagram. So let us first represent the boiler pressure T1. This is equal to 20 bar, and then condenser pressure or back pressure P2 is equal to 0.08 bar. The corresponding pressure lines on enthalpy entropy diagram are represented in this manner. So if I consider the condition of steam as superheated, it can be lying on boiler pressure somewhere here. So 1 to 2 will represent isentropic expansion in the turbine. And steam after expanding in the turbine will become wet steam. Let's say WT work is produced by turbine. Two to 3 represents isobaric heat rejection in the condenser. 3 to 4 represents isentropic compression in the pump, and 4 to 1 represents isobaric heat addition in the boiler. Let's say pump work is WP. The same process can be represented on HS diagram. So 1 to 2 isentropic expansion in the turbine, 2 to 3 isobaric heat rejection in the condenser. Please draw this line perfect vertical. I could not draw. 3 to 4 isentropic compression in the pump, and 4 to 1 isobaric heat rejection. Now in our case number 2 is also given, considering the efficiency of turbine and pump. So I need to represent actual compression and expansion processes considering the limited efficiency of turbine and pump. So if efficiencies are given for turbine and compressor, the processes taking place in those two components no longer remains isentropic. They will be actual processes, and during these processes entropy will increase. So 1 to 2 dash represents actual expansion in the turbine. Likewise 3 to 4 dash represents actual compression in the pump. The corresponding processes, same processes on HS diagram can be represented in this manner. This is nothing but critical point where dry saturated liquid line, this is dry saturated liquid line and dry saturated vapor line meet. So this way I can represent the ideal and actual Rankine processes on temperature entropy and enthalpy entropy diagram. So title of this figure will be TS and HS charts for Rankine cycle. After drawing the schematic, let us enlist all the given parameters. So in the problem, we have been given boiler pressure as 20 bar and temperature of the steam at inlet to the turbine is given as 360 degrees Celsius. Apart from that, we have been given back pressure or condenser pressure as 0.08 bar. Then we have been given pump efficiency as 80%, and we have also been given turbine efficiency as 80%, that is 0.8. Let us enlist what we are supposed to find out. So in case 1, we are supposed to find out for ideal processes the net work and the cycle efficiency. Also, we have been given the mass flow rate of steam is to be considered as unit, that is 1 kg per second. So the first thing we are supposed to calculate is net work output and cycle efficiency. In case 2, I am supposed to calculate the net work output for actual cycle and cycle efficiency for actual cycle. So let us do the calculations. To find out the net work output and cycle efficiency. So first we will be solving this problem for case 1. For ideal Rankine cycle. So first let us start our calculations by finding the different values of steam at boiler pressure of 20 bar from steam table by Mathur and Mehta. Okay. So let us refer steam table. We have been given pressure as 20 bar. So we have to refer table number 2, where corresponding to pressure, different saturated properties for steam are given. So we have to locate 20 bar pressure first. So this is 20 bar pressure. Now at this pressure, first find out the saturation temperature. This is nothing but saturation temperature of the steam at 20 bar. And this value is 212.4 degrees Celsius. That is on the PV and TS diagram, sorry, TS and HS diagram, this is the saturation temperature. Now as we can see that at 20 bar boiler pressure, saturation temperature of the steam is 212.4 bar and the temperature of the given steam is 300 degrees Celsius. It means the condition of the given steam is saturated, superheated. What we have considered initially is correct assumption. So since T1 is greater than T saturated 1, the condition of steam at state 1 is superheated. Okay, so now we have to find out other properties of steam at state 1 for superheated steam only. Hence, from steam table for superheated steam, Now we are supposed to find out the values. Oh, sorry. This value is 360 degrees Celsius. At 360 degrees Celsius. For that, we have to refer steam table. So table number 3 represents different properties of steam, superheated steam at given pressure. Now I have to locate the 20 bar pressure. Now here also I have been given the values. As you can see here, for 300 degrees Celsius and for 400 degrees Celsius. Whereas we require the value at 360 degrees Celsius at 20 bar. So I have to interpolate between 300 degrees Celsius value and 400 degrees Celsius value. So first locate 20 bar pressure. So this is 20 bar pressure, and this is for 20 bar pressure. The pressure range has changed, so I have to calculate between 350 degrees Celsius and 400 degrees Celsius. That is, I am supposed to find out the values in this zone. So I have to interpolate at 20 bar between 350 degrees Celsius and 400 degrees Celsius. I have to interpolate to get the different values of V, small h, small s at 360 degrees Celsius. So here at pressure is equal to 20 bar and 360 degrees Celsius, by interpolation I have to get all other values. So from the formula of interpolation, any unknown property at 360 degrees Celsius minus unknown property at lower temperature range to the difference of these two temperatures is equal to value at 400 degrees Celsius minus that value corresponding to 350 degrees Celsius to the temperature difference. Where x is any property. It could be small v, it could be small h, it could be small s. So simplifying this formula, x at 360 degrees Celsius will be equal to x at 350 degrees Celsius plus x at 400 degrees Celsius minus x at 350 degrees Celsius divided by, this will be 50 and this difference will be 10 degrees Celsius. So finally I will get the formula x at 350 degrees Celsius plus x at 400 degrees Celsius minus x at 350 degrees Celsius divided by 5. Now in calculator I can feed this formula in this way. A plus B minus A divided by 5. So this will help me to calculate all these properties at a temperature of 360 degrees Celsius very fastly. So after implementing this formula in calculator and calculating, I could get the value of small v1, that is a specific volume at state 1, as 0.1411 meter cube per kg, h1 as 3159.12 kilojoule per kg, and S1 as 6.902 kilojoule per kg Kelvin. So in steam table, this value will be A value at 350 degrees Celsius, and this value will be B value at 400 degrees Celsius, as you can see here. Now after finding out the V, H and S value for superheated steam at pressure of 20 bar, let us find out other properties at back pressure values. So at P2 is equal to 0.08 bar. Once again from steam table, so I will require different values like V3, H3, S3, VFG, SFG at pressure of 0.08 bar. Okay. So let us refer the steam table number 2, and in this table locate the 0.08 bar pressure. So this is the 0.08 bar pressure. Okay. Corresponding to 0.08 bar pressure, different values of specific volume, enthalpy, HF, HFG, SF and SFG I can obtain from this table. So from here, V3 is nothing but a specific volume of dry saturated steam at a pressure of 0.08 bar, and this value is 0.00108 meter cube per kg. Then H3 value, it is nothing but enthalpy of dry saturated steam at pressure 0.8 bar. This value is 173.9 kilojoule per kg. Similarly, HFG value at pressure P2 is 2403.1 kilojoule per kg. All these values are from steam table. Then S3, it is nothing but SF at P2, and this value is 0.593 kilojoule per kg, and SFGP2 is entropy of vaporization at pressure P2, and this value is 7.636 kilojoule per kg. Okay, so all these values I could get from steam table at 0.08 bar. After finding out the values at pressure P1 is equal to 20 bar and P2 is equal to 0.08 bar from steam table. Now let us do the calculations to get the values of H1, H2, H3 and H4. So H1 value I have directly from the table for superheated steam. H3 value I also have. I need to do calculations to get the value of H2 and H4. So let us do the calculations for H2 first. H2 is the enthalpy of wet steam. So H2 is nothing but enthalpy of wet steam leaving the turbine and entering the condenser, and this can be calculated as this formula. H3 plus X2 into HFGP2. In this equation, I know all the values H3 and HFGP2 except X2. So I need to do calculations for X2 first, then I can easily calculate the value of H2. So once again, in order to get the value of X2, I will be using the characteristics of process 1 to 2. So we know that process 1 to 2 is an isentropic expansion process in the turbine. Okay, this 1 to 2. And so S1 is equal to S2. S1 is entropy of superheated steam at pressure P1 and S2 is entropy of wet steam at pressure P2. And entropy of wet steam can be calculated as S3 plus X2 into SFG P2. Now I have all the values. S superheated is 6.9902, S3 as 0.593 plus X2 into SFG P2 is 7.636 kilojoule per kg Kelvin. So from here I can get the value of dry friction as 0.83 bar. .834. Okay, let us confirm the values what we have put. Okay, S1 is 6.902, S3 is 0.593, SFGP2 is 7.636. So after getting the value of X2 from equation 1, that is for H2, H2 is equal to value of H3 H3 plus X2 into HFGP2. So value of H3 we have 173.9 plus 0.834 into HFG2 is 2403.1 kilojoule per kg. So from here the value of H2 will be 2187.68 kilojoule per kg. So we have the value of H2 now, H1 and H2. Now let us get the value of H4. So for that I have to recall the specific pump work. So the formula for specific pump work WP, we have two sets, we have two different formulae for specific pump work, minus V3 P1 minus P2 is equal to H4 minus H3. Now the value of V3 is 0.00108 0.00108 meter cube per kg. Boiler pressure P1 is 20 and condenser pressure P2 is 0.08. These values I have to consider in kilopascal, so I have to add suffix 100. I need to calculate H4. I want to calculate H4 and the value of H3 is 173.9. If you do the unit calculations, you can understand why I have added the suffix 100. Kilopascal is nothing but kilonewton per meter square. This will become kilonewton meter per kg. So this becomes kilojoule per kg. And 1 bar is equal to 100 kilopascal. Okay. So the only unknown thing in this relations is H4. So I can get the value of H4 as so the value of H4 is 171.90 kilojoule per kg. So this way I could also get the value of H4 as well. Oh, sorry, the formula for pump work is, there is no minus sign, V3 P1 minus P2 into H4 minus H3. So this will become, let me correct this value, it will be added actually. (175.90 kilojoule per kg). Okay, so please remember this. The pump work formula is V3 into P1 minus P2 is equal to H4 minus H3. So this minus sign will be plus sign and the calculation for H4 will be equal to 175.90 kilojoule per kg. So now we have all the values of enthalpies, that is H1, H2, H3 and H4. So I can calculate any parameter, that is Q1, WT, Q2 and WP, in terms of these enthalpy differences for ideal cycle. So the first value will be, let us calculate Q1. Q1 is nothing but H1 minus H4, that is heat supply in the boiler. So the value of H1 is 3159.12, and the value of H4 is 175.90 kilojoule per kg. So the value of Q1 comes out so this comes out 2983.3 kilojoule per kg. Then let us calculate the turbine work WT. It is nothing but H1 minus H2. If you refer this chart, this will be 1, 2, 3 and 4. Okay, H1 value is 3159.2 minus H2 value is 2187.68. So from here the specific turbine work output will be 971.52 kilojoule per kg. And finally the pump work WP is H4 minus H3, 175.90 minus H3 is 173.9. So pump work comes out this is 2 kilojoule per kg. So I am supposed to calculate for the ideal cycle. First, W net. W net is nothing but WT minus WP. So from here 971.52 minus 2 kilojoule per kg. So W net I will get as 969.52 kilojoule per kg. So this is the required answer number 1 for part 1. Then comes the efficiency of the cycle, efficiency of the ideal Rankine cycle, and it is nothing but W net to the Q1. W net is 969.52 and heat supply just now we have calculated 2983.40 into 100. So efficiency of the cycle comes out 32.5%. This is the required answer number 2 for part 1, that is for ideal Rankine cycle. Now let us do the required calculations to get the net work output and cycle efficiency considering the actual cycle. So for actual Rankine cycle, and actual Rankine cycle is shown on the TS and HS diagram by 1, 2 dash, 3, 4 dash. Okay. So 1, 2 dash, 3 and 4 dash, and finally 1. For this cycle, we have been given the turbine and pump efficiency as 80%. So we are supposed to calculate net work output and cycle efficiency. So let us recall first the turbine efficiency. Turbine efficiency is given as actual turbine work to the isentropic turbine work. Efficiency is 80%. Isentropic turbine work is nothing but work done by the turbine considering ideal processes, and this is, we have calculated 971.52 kilojoule per kg. So from here, the actual turbine work I can get as 777 0.216 kilojoule per kg. Similarly, for pump efficiency, it is given as isentropic pump work to the actual pump work. It is also 80%. Isentropic pump work we have calculated as 2 kilojoule per kg. So from here I will get the actual pump value as 2.5 kilojoule per kg. So knowing the actual turbine work and actual pump work, now I can calculate actual net work output. This will be WTA minus WPA, that is 777.216 minus 2.5. So net work output will be, actual net work output will be 176.39 kilojoule per kg. This is the required answer, first answer for part 2. Now I have to calculate actual heat supplied during the process. Okay. And actual heat supplied Q1 will be H1 minus H4 dash kilojoule per kg. So here H4 dash I am supposed to calculate. So let us recall the pump work once again, which is nothing but H4 dash minus H3, and this value is equal to 2.5 kg kilojoule per kg. From here the value of H4 dash will be, the value of H3 will remain same in both the cases, 173.9 plus 2.5. So I will get this value as 176.4 kilojoule per kg. After getting the value of H4 dash, now I can calculate actual heat supplied. It is nothing but H1 minus H4 dash. H1 is 3159.12 minus H4 dash value is 176.4. So from here actual heat supplied during the actual Rankine cycle is something 2982.3 kilojoule per kg. So now I can calculate actual cycle efficiency. Is nothing but ratio of actual net work output to the actual heat supplied. Actual net work output is 176.39 to the 2982.3. So actual Rankine cycle efficiency comes out this value is 4. Oh, sorry. The value of net work output is 176.39. So I have to correct this. This is actually 774.716. So please let me put the correct value. 774.71 is the net work output value divided by actual heat supplied as this. So I will get the actual cycle efficiency as 25.98%. Okay, so please correct this value. 774.716 is the net work output. Now we have seen this, that in actual cycle, net work output as well as cycle efficiency will get decreased. So let us calculate percentage reduction in net work output. This will be equal to ideal net work output to the actual net work output divided by ideal net work output. So ideal net work output 969.52 and actual net work output is 774.71. Divided by 969.52. So this will come out 20.1% percentage reduction in net work output. Similarly, percentage reduction in cycle efficiency. So this will be actual cycle efficiency minus net ideal cycle efficiency minus actual cycle efficiency to the ideal cycle efficiency. It will be 32.5 minus 25.97 divided by 32.5. So this will be once again 20.1% percentage reduction in cycle efficiency. So this will be the answer as asked in the problem. So this way you can solve the problem. Here in this problem we have considered first ideal cycle, considering turbine and pump efficiency as 100%, and in second case we have considered actual Rankine cycle considering 80% efficiency of turbine and pump efficiency, and then we have compared the performance of the cycle, Rankine cycle, in both the cases.